So let's talk a little more explicitly about what useful things we can do with ideal gas processes. Um, so I want to start with drawing a system, right? So how we draw a system? Perfect. There's a system. Maybe some gas, right? And I want to talk about two reservoirs. This is a hot reservoir at some temperature T hot. Um, and then we'll have a cold reservoir on the other side of the system. This is the cold reservoir at T cold. Now, all I mean by reservoir is a body that can absorb or give heat without changing temperature. Usually, that's something very large, like a large body of water or something. Um, so let's talk about the second law of thermodynamics. Or maybe more specifically, this is a consequence of the second law of thermodynamics. Heat flows from hot to cold. That seems obvious. All right, and you can build this up statistically. You can put two systems next to each other and argue why heat should travel from hot to cold, or most likely travel from hot to cold. But you know this in your personal life, right? Hot heat does not go from cold to hot, right? If you have a cup of hot coffee in a room that's colder than the coffee does not get hotter, it gets colder, and the room gets a small amount warmer, right? So heat wants to do this. And those two Q's do not have to be the same number, so we label them Q hot and Q cold. Now, for a system that we call a heat pump, for a heat pump, sorry, not a heat pump, for a heat engine, we siphon some of that Q hot as work. We'll say work out. Okay, so we're taking some of Q hot and turning it into work out. What would this look like? Well, imagine we have, let's say, some gas, right? This could be like hot steam. And that steam could be heated with some, I don't know, some like flame, right? So, and inside of that I need some orange. And then maybe some yellow. Perfect. There's my hot reservoir, right? So we at T hot. And we let this steam go down some kind of pipe, and maybe there is a turbine. Does that look like a turbine? So right now it just looks like an acrobatic spider. Sure, there's our turbine. All right, and as the steam goes over the turbine, it causes the turbine to move, right? And you could connect that turbine to whatever, right? A sawmill or electric generator or a turntable on a stereo. It doesn't matter, right? You can turn it, and you're getting mechanical energy out of thermal energy. But part of the process here is the steam goes through and it continues, right? The steam has to exhaust. So this is the exhaust. And if the steam did some work, it lost some energy. So this is at a lower temperature now, right? And you could make this cyclic. You could have this feed back into the beginning of the system. So this is what's happening, right? We have Q hot traveling this way. So Q hot, which is some amount of energy. We have Q cold over here. And then we get some work out of this. Work can be green. Okay. So, great. This is not the only way this sort of system can go. There are all sorts of things. This is basically a steam engine, right? So let's make that go away for a second and talk about energy. So the first law of thermodynamics was basically conservation of energy, right? We can do the same thing here. We can say, okay, if this system is going to be cyclic, meaning repeated over and over and over, I need energy to be conserved. So I need energy in to equal energy out. Well, that says Q hot equals Q cold plus the work that was done. Or you could think of it like this. You could say Q hot loses some energy to work. So Q hot minus work equals Q cold, which is what's left, the remainder. This is the same thing, just solved a different way, right? It's algebraically the same. Okay. So again, this is basically a consequence of the first law of thermodynamics. And we could calculate then efficiency for the system. The efficiency of a system, we sometimes use a lowercase e, is what you get divided by what you paid. What you get divided by what you paid. In this system, what did we get? Well, the point of a heat engine, let me label it up here. The point of a heat engine is the work, right? It's the work you get out of it. So that's what I get is work out. What did I have to pay? Well, I had to heat up the steam in order to get it to do work. So Q hot is what I paid. Q cold was just exhaust, right? So Q cold was there, but it wasn't something I paid, right? I didn't put energy into Q cold. Okay, so that's interesting. So what's the best efficiency we can do here? Well, wouldn't it be great if we could just say, what if we didn't have to exhaust anything? What if we could turn all of Q hot into work out? Then efficiency would be 100%. That would be great. 100% efficiency would be fantastic. But that is not realistic. So we have to bring that back. Why isn't it realistic? Why can't we do that? Well, that's another consequence of the second law of thermodynamics, and we will get to that in a future lecture. For now, I can give you the equation for the maximum theoretical efficiency, and it has to do with the temperatures. It's 1 minus T... Where are we? T cold over T hot. 1 minus T cold over T hot. So the closer our temperatures are together, the smaller our efficiency is, right? Imagine this. What if the hot reservoir and the cold reservoir were the same temperature? Then there's no driving force, and there's no reason for heat to go from the hot to the cold because they're interchangeable at that point. Then there's absolutely no way we can get work out of this. So our maximum theoretical efficiency is 1 minus 1, which is 0, right? So if T hot and T cold are only a little different, then my Emax is going to be pretty small. And if the T hot and T cold are infinitely different, if I had absolute 0 on one side and infinitely hot on the other side, actually if I had absolute 0 on one side, this would be 100% efficient. But absolute 0 is very hard to maintain, much less reach. Okay, so that's heat engines. Let's do an example quickly. So here's an example. A heat engine takes 50 kilojoules of heat, takes in 50 kilojoules of heat, and exhausts 30 kilojoules of heat per cycle. How much work does it do, and what's its efficiency? Okay, so there, how much work what's its efficiency. So we're asking what is the work and what is the efficiency, and we're given Q hot and Q cold. All right, so let's, I like to draw the heat engine. There, and then we can label Q hot and Q cold. So there's one that's Q hot, there's Q cold, and work out. Work out is one thing we're looking for, and the heat engine takes in 50 kilojoules. So that's this, that's Q hot, right? And it exhausts 30 kilojoules. So exhaust means to expel, right? And we'll see an example of exhausting heat in a different way. Basically, Q hot and Q cold are going to change the terminology in the next system that we talk about, which is why I'm bringing this up. Okay, so what is work out? Well, Q hot is Q cold plus work out. So I can just plug in the numbers. Q hot is 50 kilojoules, Q cold is 30 kilojoules, plus this work. So work must be, come on, 20 kilojoules. You could probably see that without writing that equation, but it's useful to write it anyway. What is my efficiency? Well, efficiency is what I get divided by what I paid. What did I get? I got the work. And what did I pay? Q hot. So that's 20 kilojoules divided by 50 kilojoules. The kilos go away, the joules go away, the factor of 10 goes away. So I just have 2/5, which is 40%, right? Or 0.4. Okay. Okay, that's great. Let's do another example. Example number 9 says a heat engine does 30 joules of work and exhausts 30 joules of waste heat per cycle. What is its efficiency? Okay, that's pretty similar. Let's draw our heat engine again. It's nice to be able to visualize it. Again, our 3 arrows. This is Q hot, Q cold, and work done by the system. Okay, so work done is 30 joules, so I'll write that here. And it exhausts 30 joules, so that's Q cold. Okay, efficiency, remember, is work divided by Q hot. So I'm going to need to know Q hot before I can go any further. Looks like if I'm losing 30 joules here and 30 joules there, I need to put in 60 joules for energy to be conserved. And then I can solve this. So that's 30 joules of work done divided by 60 joules pumped into the system. That's a 50%. Okay. Great. What else can I do with this sort of system? Well, there are times where I would prefer a cold system to stay cold or to get colder, right? Imagine a refrigerator, right? So I have a box, and the inside of that box I want to get colder than outside, and that's not going to happen naturally, right? Naturally, systems want to come to thermal equilibrium. So I'm going to have to do some work to make that happen. That's a thing called a heat pump. So let's write about that. So what's a heat pump? Well, it's the same system. It's the same kind of setup. But now I would prefer that the heat go the wrong way. So this is still Q hot, heat exchanged with a hot reservoir, and this is still Q cold. Again, this is still the cold reservoir, and that's still the hot reservoir. But again, I want energy to go the wrong way now. That's not going to happen naturally, so I'm going to have to do some work on this system. Sometimes we say work in to make that happen. All right. Again, this is like a refrigerator. So the fridge is actually the cold reservoir, and I want to pump heat out of the cold reservoir. And what I do is I do some work on a system like Freon gas. I compress the gas, and when the gas expands, it takes in some energy. That's Q cold. And then for the system to come back to its original state, it has to exhaust some energy. It has to exhaust some of that energy, and that's the coils on the back of a fridge. If you've ever felt when a fridge is running, the back of the fridge is hot. That's Q hot dumping back into the room. All right. So what's happening is you're actually heating up the room by pumping heat out of the inside of the fridge. Right. So imagine this: if you open a refrigerator, you're making the system work harder. You're not actually cooling down the room. It'll feel cooler right in front of the fridge, but if you add up the heat lost by heat going from the room into the fridge through the open door, and the heat gained by the room dumped by the exhaust in the back of the fridge, you're actually heating up the room. So opening a fridge in your room is actually heating up your room. That seems counterintuitive. It's just that they're separated by some distance. Okay, so again, this is a heat pump. So what can we do? Well, we have energy concerns again. We could say the energy pumped out, Q hot, is equal to the energy going in, which is Q cold, and the work put in. Look at that. That's the exact same equation we had before, and that's because every arrow is backwards from what it was, right? So everybody that was on one side is now on the other side of the equation. Averages out to the same equation. So there's our heat pump. What about efficiency? Well, we define it the same way. We still define efficiency as what I get divided by what I paid. There. So what do I get? Well, that depends on what I want here. For a fridge, I want Q cold, and what I had to pay was the work that went into the system. But there's another system where you could use a heat pump to heat something up. This is sometimes what's used to heat high volume systems. So like the heater for a large building is maybe not a furnace, maybe it's a heat pump where you're actually pumping heat from outside the building in, right? So up here would be my heat pump. I'll say heater because it's a heat pump either way. So this is for a fridge. We'll say or Q hot over work put in, and that's for a heater. Again, it's the same system. It just is the difference between I want my fridge to stay cold on the inside or I want my fridge to heat up my room. So a fridge doesn't heat your room very efficiently, but there are other systems that would heat your room more efficiently by pumping heat out of the room. Again, you don't usually do that for a heater because it's easier to make heat other ways for that scale, like a dorm room size. But for a big building, it's actually more efficient to use a heat pump system like this rather than like a furnace. Okay, so we don't call this efficiency because it's not a percentage, even though it means the same thing. We're defining it the same way, what we get divided by what we paid. But because it doesn't come out to be between 0 and 1, we call this the coefficient of performance, or a COP. All right, and the second law of thermodynamics gives us another theoretical maximum for this. That maximum is, let me find it real quick. So the maximum for this is T cold divided by T cold plus T hot. That's for a fridge. Or it's T hot divided by T cold plus T hot. That's for a heater. Okay. And again, the origin of that is the second law of thermodynamics. I'll talk about why that is in just a little bit. So let's do an example. Let's talk about not that. Let's talk about this one. Example 10 says a certain fridge requires 20 joules of work and exhausts 70 joules of heat per cycle. What is its coefficient of performance? So, as I am apt to do, I'm going to draw my system and the heat reservoirs. It's a little wonky, but who cares? Okay, and if this is a heat pump, so it's a fridge acting as a, or sorry, a heat pump acting as a fridge, I have heat going this way, I have heat going this way, and work going in. Again, heat exchanged with the cold reservoir is always called Q cold. Heat exchanged with the hot is Q hot, and this is work in. So the fridge requires 20 joules, come on, of work, so that's 20 joules here, and exhausts 70 joules of heat. So here's what I want to say. The word exhaust, that means leaves the system. So that's this 70 joules. All right, and again, remember for a refrigerator, the back of the fridge is giving off heat. That's not useful heat, that's just exhaust, right? So Q cold is the thing that I actually care about. So let's ask the question then, what is the coefficient of performance? Well, remember, coefficient of performance is what I get divided by what I paid. For this system, what I get is Q cold, and what I paid was work in. Okay, so work in is 20 joules. What's Q cold? Well, Q hot equals Q cold plus work put into the system, so that's 20 joules equals Q cold plus, 70 joules equals Q cold plus 20 joules. So Q cold must be 50 joules. Great, and we're going to plug that in up here. So 50 joules divided by 20 joules. The joules go away, the zeros go away, so it's 5 halves, which is 2.5. That is unitless, right? Joules over joules is unitless, but it doesn't make sense to call this a percent because it's bigger than 1, right? Coefficient of performance doesn't have to be bigger than 1, but it doesn't have to be smaller than 1. Efficiency for the heat engine was definitely between 0 and 1. But for a heat pump, it doesn't have to be, which is why we don't call it efficiency, because it doesn't make sense to call that a percentage. So we just leave it as a number, but it still is the case that bigger is better, right? I want to maximize what I get and minimize what I pay. Okay, so that's good for this idea